Hello, everyone. So yesterday we introduced the quantity angular momentum, right? And we found that the angular momentum of a rigid object rotating about a fixed axis is given by I omega. Notice how that works with the linear analogy of mass times velocity. It's rotational inertia times angular velocity. So for reasons which will become apparent momentarily, let's take the derivative of both sides with respect to time. This is the rate of change of angular momentum, right? And over here we have the derivative of I omega with respect to time. But for a rigid object rotating about a fixed axis, the rotational inertia would be a constant. It would just depend on how the mass is organized, right? And it would stay the same way the whole time. So that can be factored outside of the derivative. And then look what we have left. We have the derivative of the angular velocity with respect to time, which is, of course, the angular acceleration. But now look what we have. We have rotational inertia times angular acceleration. Well, I hope you remember that that is net torque, right? Net torque equals I alpha is Newton's second law. So this gets us to see that the rate of change of angular momentum is equal to the net torque acting on the object. And this is actually closer to Newton's second law rotationally, as stated by Isaac Newton. You might remember that linearly, he stated that the net force acting on an object is the rate of change of momentum. So this is kind of the linear version of that, right? The net torque is equal to the rate of change of angular momentum. Right, so it's analogous to this, which is really the way he wrote it in the Principia. Now, what if the system is isolated and closed? Right? Remember that isolated means no external torques in this case. Right? And closed means that the mass doesn't change. So I suppose no piece of the object breaks away or something like that. In that case, there would be no net torque. Any torques between pieces, there'd be equal and opposite torques, Newton's third law, and those would cancel out. Right? So with no external torques, and that means that the rate of change of angular momentum would be zero. Well, if the rate of change of angular momentum is zero, that means your angular momentum has to be constant. This is what is known as the law of conservation of angular momentum. In any closed, isolated system, the angular momentum is constant. The angular momentum is conserved. Right, now notice, though, it needs to be closed and isolated. No external torques here. Okay? Only the torques can be between objects in the system. Now, watch this little Simpsons video here.
Bart, do you have your slingshot?
No, sir.
I see it in your back pocket.
Just don't stretch it out.
I was once a boy, and like all boys...
You like all boys?
Shut up! A child is in danger under my aegis. Run, Ralph! Run!
Okay.
Time to do what I've never done as principal. Something.
Watch what he does.
Skinner's spazzing out!
I'm not spazzing out. I'm using the principle of conservation of angular momentum to turn the container.
That is so cool. That's the kind of stuff they should teach in school.
We do teach it in school. You're too busy eating sugar snacks and horsing around.
He's right. Learning can teach you things. Education rules.
Okay. So what was going on there with Skinner? Right? And this is actually good physics. So let's make our system Skinner and the crate filled with the infinite number of grand pianos. Right? So that is a closed, isolated system, which means that the angular momentum was conserved. The initial angular momentum of the system was equal to the final angular momentum of the system. Well, initially, there was no angular momentum. Right? Neither Skinner nor the crate was rotating. After Skinner started running in one direction, right, then they both had angular momenta. So the final angular momentum of Skinner and added up with the final angular momentum of the crate have got to add up to 0. And that means that the final angular momentum have to be the same size but opposite direction. Did you notice in the video that Skinner ran in one direction and the crate turned in the other direction? Now, each one of these would be rotational inertia times angular velocity. And so these things have to be equal and opposite in this case, right, in order to add up to 0. But did you notice here that Skinner was running a lot faster than the crate was turning? Well, that's got to do with the two things that make up angular momentum, rotational inertia and angular velocity. Right? So Skinner had a small rotational inertia, comparatively, but he had a large angular velocity as he was running in a circle fast. On the other hand, the crate would have a large rotational inertia, being as massive as it is, and therefore it only needed a small angular velocity for these linear momenta to be equal and opposite. So a lot going on in that video, and the physics in it was really kind of tight, right? So Skinner ran in one direction, it rotated in the other direction. Skinner ran fast, the crate only turned slowly because of their various rotational inertias. Second example, the spinning professor. Watch this video.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get a nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
That's kind of a fun one, right? So what's going on there? Well, again, if we make the system the spinning professor and the chair and everything, right, then it is a closed, isolated system. And therefore, the angular momentum before has to be equal to the angular momentum after. Now, in each case, that angular momentum is going to be the rotational inertia times the angular velocity. Okay? What the system had before has to be equal to what the system had afterwards. But what did he do in that video? He took his arms, which were out, and he pulled them in tight. Right? Well, what does that change? Well, that changes where the mass is, right, with respect to the axis of rotation. It moves the mass closer to the axis of rotation. That reduces the rotational inertia. So he started out with a large rotational inertia and therefore a slow angular velocity. But after he pulls his arms in, he now has a smaller rotational inertia and therefore must have a proportionally larger angular velocity in order to get everything to balance out. And as soon as he put his arms back out again, the opposite thing happened. Right? Pull them back in. And this is something that, if you've ever watched, gymnastics, diving, those kinds of things, right? Those are people that know this innately, right? They tuck when they want to spin faster. They lay out when they want to spin slower. Right? So as you're watching the Olympics or you're watching some gymnastics world championships, right, you can see the conservation of angular momentum quite often in action. Okay, now let's look at a problem where we have particles and conservation of angular momentum. So in this case, we have a planet, right, and the planet is orbiting around a sun. Right, and I want to compare the speed of the planet at y, over here, to the speed of the planet at x. Okay, how will those speeds compare? Well, if our system is the planet and the sun, right, then it is an isolated closed system. And therefore, the angular momentum initially and the angular momentum finally have to be equal. In this case, our angular momentum initial will be at x, and our angular momentum final will be at y. So here is ry, right? This is the distance from the sun to the planet at y. At this point, if we're assuming here that it's rotating counterclockwise just because, right, the velocity will kind of act tangent to that. So this is Vy. Meanwhile, over at x, right, there's Rx, and there is Vx. Now, using the angular momentum equation we developed yesterday for particles, we get Rmv sine theta for each case. Okay, now note here, this is Rx and Vx, and this is Ry and Vy. Notice I didn't have to subscript the m's because the mass stays the same. So those masses are going to cancel. And because of the points that I picked, and I picked the kind of the fancy points, the nearest and the furthest point from the sun, okay, perihelion and aphelion, you're at perigee and apogee. Okay? Because I picked those points, the velocities are tangent to the radii, which means, in other words, the angle in between is 90, and the sine of 90 is 1. So that means we are left with the velocity at y is going to be equal to the ratio of Rx to Ry times the velocity at x. But let's look at this ratio. Right, from the diagram, it's quite obvious that Rx is bigger than Ry. And that means that the velocity at y has got to be faster than the velocity at x. Right, you're multiplying here by something larger than 1. Right, so the velocity at y is bigger than x, which is actually how I drew these arrows, knowing as I did how the problem would turn out. Right, so faster here than there. Note that what that is telling us is that the closer the planet gets to the sun, the faster it will go. So as the planet moves from x around to y, it's just going to get faster and faster and faster. Now you might remember that as something called Kepler's second law. So this is really an angular momentum approach to kind of proving Kepler's second law. Right? That was the law of equal areas and equal times, but the corollary was planets move faster the closer they get to the sun. Right? Now, Kepler couldn't prove that. He just knew it was, right, from measurements that he made. But it's kind of an interesting way of looking at things and comparing them. And notice here we are using the point particle versions of angular momentum. And don't be sloppy, it's Rmv sine theta, even if the sine thetas are going to cancel because the angle is 90.